was out sick this past week and this week. So he's been sending old letters he did, but I can't probably read the board that's not just relying on the handouts.
Well, this is going to be a problem. I can't minimize it. Oh, but I can go this way. And I just want to go to Canvas and go to our Canvas page. Oops, not VCU. Has anybody looked over the homework set? 3, maybe some problems from 3. You took a look at those? Good. I can help us think about some of those. Did you watch the video of me doing optimization with more than one choice variable? I was talking there about some of the differences between one choice variable and 2 choice variables. The biggest one I would say is the second order conditions have changed. They're a little bit more complicated with more than one choice variable, but the first order conditions are pretty much the same. Before, with one variable, it was take the derivative of the objective function and set it equal to 0. Well, now it's take the partial derivatives of the objective function and set it equal to 0. That's pretty much the same thing. Should I open up? I'll open up not the video, but the lecture notes that correspond to the video. Take a look at those. Did you have any questions in particular from something I did or said back when I recorded these? It's been probably 3 or 4 years ago. It's during COVID, I think, when I recorded these. Does anybody have any questions about? A lot of this was just examples of why we might want to optimize something, like profit, cost. That still counts as optimization. If you're minimizing something, that still counts as optimization. You know, it looks the same. The math is fact exactly the same until you get to the second order conditions. The first order conditions are exactly the same, whether you're maximizing or minimizing. The only difference will be the second order condition. Yeah. This is what me on the video would have talked to you about, that there's only corner solutions here because there's no boundary. I mean, you could establish a boundary if you want, but I think for this set of problems, we're going to separate. Unlike with one choice variable, we had some intervals maybe, or where there was just an open where the choice variable could be constrained or maybe unconstrained, and it really didn't matter. It didn't change much. It will change a lot for these types of problems. Problems with 2 choice variables, it matters a lot whether they're constrained or unconstrained. So I'm going to wait and talk about constrained after the midterm, I guess, just to split it up that way, and just do unconstrained problems that look like this. I'm choosing x and y. There could be any real number, and this is the function I'm trying to maximize is this f of x and y. You guys have already seen this. Any questions about the first order conditions? Something like this. I like to write it this way: f with the little subscript of x equals to 0, f with little sub y. Sometimes I call this FOC1, the first order condition, FOC2, the second first order condition, just because that's the order in which they're there. Yeah, you can almost tell that these two are roughly identical expressions of second order conditions, but this is kind of the first real math that you get from this lecture that maybe you didn't have already. Was that why did I do min? We should do max first, right? Let's do max first. Good news is these are sufficient. Remember, sufficient second order conditions are somehow better because you know you're done. If you found this, if something satisfies the sufficient second order condition, you know you have an answer, perhaps even the answer. Okay. And those are for maximization that the second order derivatives should be negative. And we talked about this before that it's redundant to also check FYY being negative, but you can do it if you want. If fxx, which is the second order partial derivative with respect to x, if that is negative, and this holds, then it's automatically true that fyy will also be negative. You can check it if you want, but it's not gonna be so important. And okay, you might wonder where this comes from. I'm sure me of the video would have talked about this. This is the determinant of the Hessian matrix, or two of function of two variables. And that determinant should be positive. This is part of what makes it the sufficient condition, that this is strictly negative, and this is strictly positive. You guys have questions about that? Remember, you only look at this after you've satisfied the first order conditions. If I give you a problem, first thing you do, try to solve the first order conditions for optimization. You might get a candidate then for X and Y. Now you're looking at this candidate. Is it indeed a maximum? That's when the second order conditions would be relevant. Questions about that? And here's min. The only difference is that this is flipped. This is not flipped. Determinant is still positive. It's positive in both cases. The only thing with minimum is that the second order partials are positive for min, negative for max. You've already watched me say this. Do you want me to go over this again? Okay, so you want me to go over this? Okay, the reason why they're more complicated is this is really just intuition that I'm providing on this slide here. That what it means to be the top of a function, like the hill, the top point of the hill, you need to know more about the curvature of the function to really say if something's at the top of the hill. And I've drawn a picture here. I've drawn a picture here that says you might think that this point is at the top of a hill because when you look at it at from the blue perspective, that's the y-axis perspective, it looks like it's at the top. When you look at it from the red perspective, that's the x-axis, it looks like it's at the top. So both the first order conditions in x and y look like they have the right curvature to suggest that this point here is indeed a maximum. But it's not a maximum. The reason it's not a maximum is that the function here, imagine there's a third dimension that goes up or in, up, out, or down in. And this, along this green dimension, the function is growing, right? So this can't happen in one dimension. It's either a hill or it's a valley. But this sort of saddle where it's coming out at you from some other way, it can only happen when there's more than one choice variable. So if x and y are both choice variables, and you thought this point was a maximum, you'd be wrong. Because actually, you can make the function higher by going in this direction, where both x and y are increasing. Or wait, which one's positive? Yeah, this x is positive, y is positive. So here in the fxy direction, you could sort of incorporate. Sorry, you can interpret this cross partial derivative as how does the slope of x change as y increases, and it's positive here, which means this kind of curves up. So this curvature up here, which is what makes it not a maximum, is why we have to check for that Hessian part, that determinant of the Hessian part, which was here. This part here. That's really just an explanation for why this part here matters. It's not enough to just look at fxx and fyy. You have to look at xy, but it's not like any amount of fxy will destroy your function and make it a saddle point. No, really, the magnitude of that has to be less than this, so this minus this has to be positive. It's basically saying that diagonal type curvature can't be so high, it has to be small. And then as long as it's not so high that cross partial curvature is small enough, then what you thought was a min or max is actually a min or a max. Yes.
Does FYY also need to be positive?
Yes.
Okay.
Yes. Remember I said that was redundant.
Okay.
So it actually must be true, and it always will be true if these two things are true.
Awesome.
I wonder if it would be clearer just to write it. What do you think? In the future, should I just say fxx positive, fyy positive, and this? Then people aren't going to wonder, why are you choosing x and not y?
People are gonna think that they got both.
Well, you don't have to do both, but they're both true. But so this is a more parsimonious, that only has as little as you need. But of course I could have added fyy being positive, and it still would have been a true statement.
Okay, and I understand the hash matrix determinant to be greater than 0 proves that.
Yeah, that's what I was telling you.
That wasn't.
But this is to sort of eliminate the possibility of a saddle point. That's what this part is. Because if you look at these saddle points, what's really happening is here, this fxy is too big. If it gets too big, that's bad. Yeah.
The structure of a saddle point have the true maximum anywhere, or is it impossible?
Well, it depends on the rest of the functions. I've only shown you. I'm taking a lot of liberties here, which is really thinking of this the neighborhood of this point. And I'm not even saying anything that happens outside this neighborhood. It could be that somewhere way over there, it has a true maximum point somewhere. But is this point a max? No. Is it a min? No, it's a saddle point. It's kind of got elements of both maximum and minima, but in reality, it's neither. Good question. So this is everything that I'm writing here is what I was saying in words. I wasn't reading off of it, but that's what we need to, that's what you need to check. I think the best thing to do is some examples. Math examples are the best way to know what it is you're supposed to do in these cases. But before we get to some examples, let's talk about what it would be like if there were 3 or more choice variables. You could imagine a function with not 2, but lowercase n choice variables. And then this is an objective function with n choice variables, n inputs. The first order conditions are the same. It just extends where the first partial derivative with respect to the first variable has to be 0. Partial with respect to the second variable has to be 0. Every variable, the partials have to be equal to 0. That's how you know it satisfies the first order conditions. There's this other term that you might hear, it's called a stationary point. Stationary means it satisfied all the first order conditions. But what about the second order conditions? Well, you don't just have x and y here. Before you only had x and y. Now you have x1, x2, x dot dot dot, xn. We can still say something about it, which is it's a sufficient condition for maximization if f is concave. Because if you think about it, concave is pretty much the same idea as being the top point of a hill. If a point is the top point of a hill, it's going to be the maximum, no matter how many dimensions you're thinking of. So f being concave is equivalent to the Hessian matrix being negative definite at the stationary point. A negative definite matrix is something I think we talked a little bit about a couple lectures ago. Determining whether a Hessian matrix is negative definite. My recommendation for that, there are multiple ways to do this, but my recommendation is to look at the leading principal minors of the Hessian matrix. And for negative definite, it would need to alternate in sign. Whereas for positive definite, they would have to all be positive. And if you think that's confusing, you can think of the fact that you had a negative, then another negative, two negatives makes it positive, but then a third negative makes it negative again. That's why the negative one is alternating in sign, negative, positive, negative, positive. Whereas the positive one doesn't alternate, it just stays positive, 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 positive. I really don't expect me to ask you to do this in a quiz or something. It would take a lot of time for you to, like if I gave you a really big problem with lots and lots of choice variables, it would take you so long that I sort of don't expect you to do that. It's good if you know this concept though, like, I'm teaching you optimization. And I'm going to be doing a lot of examples with just two choice variables. Could you do it with more than two? Yes. Yes, you could. I would like for you to know how to do it, how it would be done with three choice variables or four choice variables. But for me to actually ask you to do it on a quiz, it would just take too much time. I don't want you to spend all that time doing it. For an exam, I also think maybe not. I don't want to promise that I won't give you something with, let's say, three choice variables. Four seems crazy. I'm not going to do four, but maybe I would do three. I might try to make it kind of easy if I am going to give you a function with three variables, just to make the math work out so that you're not spending all your time. Does that mean, are you somebody worried about that? Like, oh, just said we have to do it with three choice variables. Therefore, we need to know exactly what it means to have a negative semi-definite or positive. I said semi-definite, huh? Yeah. I really think that's the kind of thing I would maybe do in an exam, but not quiz. So if you want, since the next thing we're going to have is a quiz, I won't give you a lot of examples with three choice variables, but we can if you want in between the quiz and the exam, which is next week. Yeah.
What topics will be covered in the group?
Somebody asked me that too. Emilian wanted to know, and what I told him was the best way to consider what's on the quiz and what isn't are by these modules. And I kind of think 2, 3, 2, 4, and 3, 1, 3, 2. Okay.
Will it cover 3 weeks, like next Tuesday?
Yeah. But not before the quiz.
Yeah, but we can anticipate being on the midterm.
Yeah,
Okay.
it's not that hard.
Yeah.
I think maybe there's a few concepts there if you've never heard before. It's like it's worth it to go over.
No, I was just curious if I should start looking at it on the practice before.
Not going to be on the quiz, but yes on the midterm.
When is the next quiz?
Thursday, 2 days from now. 2 days from now. The midterm is 9 days from now. Hello.
So the next quiz will cover.
The next quiz will cover. Do you want me to write this down?
Yes.
I don't have a lot of space. I could write it over here. Right over here. Quiz 2 on Thursday. Quiz 2 Thursday. That's what, September 25th. And that could cover the lectures in 2.3, 2.4, 3.1, 3.2. About that. And then the midterm is exam is on also Thursday, a week after. It might actually be November. Oh, sorry, October.
Yeah.
October what?
I don't know. but
I
it's definitely
think
October.
The.
Same
I won't say it.
October something, and this could be all modules. All modules, 1, 2, and 3. Right. But this can be open book, open note. That's fine. And sort of all class periods. So we actually have 75 minutes for this class, but I want to give you all 75 minutes to do it. So maybe I'll try to get here a little early that day. Pass out some scrap paper. You need scrap paper, just like blank paper. You can bring it, but I'll provide some if you don't have it. The jelly calculators. Yeah, if you want them, you have them. What,
Yeah, that's actually what says best way to study for like practice exams. I saw there were a couple of them.
Yeah. Or, I mean, at least diagnose how hard. Those are gonna be kind of hard maybe, but. Actually, the midterm exams were Econs. They were a bit longer though. They were longer. Back then. Instead of having twice per week, it was once per week class, it was longer class. So this midterm exam for you guys, it's gonna have to be shorter. It's only 75 minutes. Open book now. Open book, better. Okay, and did anybody find out what October day is? It's
Second.
Second. Yeah, that was his plan. So today, let's make sure you're ready to go for the quiz. It'll also help you for the exam because it's material that's on both topics. Good question. Where were we? I was saying like for a quiz, I'll only give you 2 choice variables. For the exam, I also only have 75 minutes, so I might not, but I could give you something with 3 choice variables. Here, does the me of the video talk about this? I think must have if it's on here. We had this concept of eigenvalues from the previous lecture 3.1, talked about eigenvalues, and that's a kind of a maybe quick, maybe not so quick way to tell if a matrix is not semi-definite. Sorry, not like definite, but semi-definite. Semi-definite is a weaker condition than being definite. And that means that every definite is also semi-definite. But this weaker condition of a semi-definite matrix, one way to find that out is if every eigenvalue is non-negative. Makes it semi-definite. Positive semi-definite. Whereas the opposite, negative, means non-positive. It can be 0, but non-positive. For example, here is H. I'm thinking of it like a Hessian matrix because oftentimes you'll only be doing this with the Hessian matrix, but here's a matrix called H. The eigenvalues of this are 1 and 0. So H is positive semi-definite. 1, 0, 0, 0 is a positive semi-definite matrix for the Hessian. And this would satisfy the necessary SOC for minimization, which are back on this previous slide. The necessary second order conditions for minimization, the Hessian is positive semi-definite. You notice that's the only difference. Definite, semi-definite. Definite, semi-definite. That's the difference between sufficient and necessary. Does anybody have any questions about what that means? Sufficient, necessary, and how like it might matter. Because if you found that the necessary condition holds, that's good. That means it's a real candidate for, let's say, maximization. If you found this, that means that point could be the maximum. You're still not absolutely sure, but you can't rule out the fact that it's a maximum. If the necessary second order conditions are not met, then you can rule out it being a maximum. It can't be a maximum. That's the point of the necessary condition. In my mind, they're weaker than the sufficient conditions, which say, if these are satisfied, then we know for sure it's a maximum. Okay. Want some example? Was anybody confused about where the eigenvalues of this came from? You know, there's this like equation you can write to calculate the eigenvalues. Do you want to see it? Do you want to see it? Anybody want to see the equation for calculating eigenvalues? Good. up with this board. And I'll do it. The trick to do is subtract lambda from all diagonal elements of the matrix. So this becomes 1 minus lambda, 0, 0, minus lambda. And then take the determinant of this and set it equal to 0. This is the way you'll always find all of the eigenvalues by doing this, including complex eigenvalues, which will come into play later. Right now, they're hopefully real. If I'm being nice to you, they're real. How do I find the determinant of this? It's 1 minus lambda times negative lambda, put that equal to 0. What are the solutions to this? It's obvious to me that lambda equals 0 is the solution and lambda equals 1 is the solution to this. You can resolve this however you would like to do algebra. Is my pen not dark enough? Need more ink in my pen? I don't know what to do about that. But the solution to this, like there's no factoring, it's just this or this has to be 0. This is 0 when lambda equals 0. This is 0 when lambda equals 1. So lambda equals 0 or 1. Okay. So if you get to ooh, you know what would be fun? Fun for me, I don't know if it's fun for you. Work backwards and think of what function might give you a Hessian that looks like this. This is sort of like backwards thinking. Oftentimes I give you a function, I say, find the Hessian matrix for this function. Now I'm going backwards. Given this Hessian matrix, what do you think, what function would give rise to a Hessian matrix that looks like this? Make it f of x and y. Anybody have any? Just throw it out. If you know.
Over 2
Ah, I like that.
plus whatever.
Plus what?
X. Well, I guess C technically, but
Yeah.
anything that's not X.
Wrong. Is that okay?
Yeah, that's fine.
It's okay. Do you see why? Once you take the second derivative of this, it'll be 0. So you could have linear terms here.
Yeah,
you could have,
it's not
you
X.
could have, right. I just want to, what you said, the way you were thinking
Yeah,
is
yeah,
perfect. You just forgot about, because these are not derivatives, these are second derivatives. You could have linear terms here, as many linear terms as you want. They disappear in the Hessian. And the takeaway there is, we're not talking about how the function behaves in some linear sense. Who cares about the linear stuff? We only care about the curvature of the function. The Hessian matrix measures the curvature of a function, and linear terms don't affect it. Okay? So this function here, if I asked you to find the Hessian matrix of it, you'd get this. What if we were like, what's a minimum? No, yeah. Okay, yeah, minimum point on this is going to be, yeah, we could find it. Could find a minimum here. Excuse me. Okay. Oh gosh, there's not going to be a minimum. Do you know why? We can't find a minimum. Because no, x is fine. X is fine, but not y.
Oh, you're right.
If I take the derivative of this with respect to y, I get -3. What is my first order condition? F of y should be equal to 0. It's never equal to 0. So if I gave you this function and I asked you find all the maxima and all the minima, by the way, that's the plural of maximum, minimum. You just turned it to A. All the maxima and minima of this function, your answer quite simply would be none exist. And the reason that none exist is because the derivative with respect to y is -3, which is never equal to 0. Okay? Kind of an easy question to answer. Now I have to get rid of the y. I'm going to change the problem in getting rid of this y.
And,
Pardon?
and it should still work with the problem
Yeah.
here.
Yeah. If I said, oh, so this is a little weird because there's no y in it, but I'm a little reluctant to go down this path because it's like a pathological function where it's a function of both x and y, but y doesn't appear. Yeah, so that's a little weird.
Then is it even a function of y?
Right.
Yeah, that's.
I mean, it is if I say it is.
There's no y.
There's no y. So for any value of y, it gives the same point. So what you're going to find is maybe this is worth doing, because that's kind of the point, that we have the necessary conditions are satisfied, but not really the sufficient ones. What'll happen if we take the derivative of this with respect to x? We're gonna get x plus 4, and if the first order condition, the first one, I use a colon there, just like say what follows it is this. This, I often like arrows here just to say that the equation doesn't stay the same. Is that x equals -4. Oops, I meant equals 0. Now arrow, x equals -4, right? Well, what's y? I don't know. For any value of y, could be anything. This is bad math. You would say y is any element of the real numbers, right? Y could be anything. And we would have something which satisfies the first order conditions here, because after all, f of y is always equal to 0. Y isn't in there at all. It's kind of weird. Well, still f y equals 0. So anything, this would satisfy all of the first order conditions for any y. If we took the Hessian, we'd get this. If we started to do the second order conditions now, the second order conditions. This is the first order, second order conditions. We get a matrix like this, which is weird. It's because the problem is weird. We could say, because the eigenvalues are 0 and positive, but never negative. That's what non-positive means. You're okay with that? No, sorry, non-negative. Non-negative. This is what we mean by non-negative. Remember that was so that's right. That means H is positive. Can I abbreviate it this way? Positive semi-definite, which means the necessary conditions, necessary second order condition for min have been met. Not the sufficient though. And this kind of makes sense. You wouldn't really take any of these points, x equals -4, y equals 0, and say, aha, we've got it. This is the unique minimum point of this function here. No, because y could be anything. And it would be another minimum, right? There is no unique minimum of this function. And you can kind of see that because this isn't positive definite. It's positive semi-definite. If it were positive definite, then we would have not the necessary, but the sufficient second order conditions. And then we would say, whatever it is we found that satisfied the first order conditions is indeed a local minimum. Did you see I snuck the word local in there? Yeah. Local min. What if you're like, but we need to know if it's a global min? We actually would also know it's a global min if the Hessian is positive definite everywhere, right? So basically it's a local min if it's positive definite right at that point. It's a global min if it's positive definite everywhere. And because the Hessian doesn't change, there are no x's, there are no y's in there. It would be true for the whole function. By that I mean local, what we're really talking about now is local concavity and local convexity. Right? Concave it's to me, I just sort of think this is synonymously with the minimum. Wait. maximum. Right? And so like if you have local concave, then you also have a local max. If you knew a function was globally concave, that means it's concave everywhere, then this maximum that you would find is also a global max. They sort of go together that way. Same thing with convex and min. Where you can add this sort of adjective of local or global, and it will apply to both. So maybe this was a weird example that was just to illustrate to you how you can find the eigenvalues of H and say something about whether it's positive semi-definite. I kind of don't recommend that for finding out, not that something's positive semi-definite, but just positive definite or negative definite. For that, I still recommend using what I would call the leading principal minors, which is like the top right parts of the matrix. So let's see that in action for like a better example. This wasn't the best example. This is a much better example. Did somebody already watch me do this in the videos? That's going to be the same example that I did on the videos. I just don't know if that's a problem. Is everyone okay with that? If I do the same example right now, then the me of the past did on the videos. Okay? Okay. Here is a pretty straightforward. I say straightforward because it's quadratic. There's nothing crazy going on here. No logs, no fractions even. It's not a max or a min. It's only a max. Two choice variables. What's the first thing we do?
First order derivative.
First order conditions, which are the partial derivatives. Yes. So you're right. I'm not saying you're wrong. I'm just calling it something else. I wish I had something to write on while we can still see this. It's not going to be perfect, but okay, if I raise this and then work underneath it. Alternatively, I could go all the way over there and write. But that doesn't seem great either.
If you just copy it to the top of the board.
Yeah, that's probably the best thing to do. I mean, even if I like leave it on for a while, it's probably okay. Yeah, it's good. It's a little weird, but I think you guys are okay with that. Or do you want me to rewrite it? Let me rewrite it. It's right at the edge. I'm gonna rewrite it. 10 minus 2x squared minus 3y squared plus 2xy plus 5x. First thing we do, first order condition number 1, that's the x one. What's the partial derivative of this with respect to x? Okay. Correct? Plus 2y plus 5, very good. Set that equal to 0, right? What do we get? Actually, let's wait off on what do we get. Let's not try to solve it yet. That's a good lesson. Just one first order condition generally is not enough to solve. We need all of the first order conditions and then solve. Let's look at the second one. What's that? Somebody else who hasn't answered yet? Yeah, that's this one. Minus 6y, very good.
Plus 2x.
Plus 2x equals 0. Now we can solve. One first order condition wasn't enough, but two of them together is enough. And generally this will always be true because you'll have two equations and you'll have two unknowns. The two choice variables have the two unknowns. So we can solve this any way you'd like to solve it is fine. I don't care. You don't have to use Cramer's rule. Cramer's rule is not necessary. You can use substitution. Probably the fastest way to do it.
Can you use Gauss-Jordan?
What's that? Gauss-Jordan?
You never heard of that?
No. Is it about matrix manipulation somehow?
Yes, matrix manipulation.
Ah, okay.
But X.
I mean, I knew Carl Friedrich Gauss, one of
Yeah.
the greatest mathematicians of all time, if not number one, the greatest.
It's really good if you have like 3 or 4 variables that you're
Okay.
dealing with, because then you can eliminate all of them and you don't actually have to do the algebra.
Makes sense. But I don't want to teach that to people who
Okay.
don't need it. Let's just use substitution here. Let's solve for x in terms of y or y in terms of x and then go from there. How about using this? We'll add 6y to both sides and divide by 2 and get x equals 3y. Okay. The point of this is now substituting in where there previously was an x, we replace that with 3y and get an equation from here. Plugging that into there and getting, instead of negative 4x, we get negative 4 times 3y plus 2y plus 5 equals 0. Now we can solve for y. We do some math here. Negative 12 plus 10 is negative 10y. I'm going to add that to both sides and get 10y equals 5. Then divide both sides by 10 and get 1/2 equals y. Did you guys get that too? Great. You checked. You were a good check on me. What is x then? X is 3 times y. That's 3/2. So we have this point here. Sometimes you see it written this way. Xy equals 3/2. You okay with that? This is just like thinking of it as an ordered pair. It is an ordered pair. X is the first, second, y is the second. That is the order. It's an ordered pair. You don't have to write it that way if you don't want. But are we done?
No,
No, that's only the first order condition. This whole point of this lecture in these classes is to also ask you to do the second order conditions, right? How should we think of those? We want to go strict, yeah. Yep.
X6, Y.
Yep. You want to, you know what I think we should do is this, find out what fxx is first. Knowing that we've already written out fx right here. So we just take the derivative of that with respect to x. What do you get? Negative 4. This is easy because it's all linear. fxy, also known as the cross partial derivative, it's 2. You can see it's 2 here. You can look here or there to see that it's 2. And fyy equals, make sure you're paying attention, negative 6. Now we're ready to talk about the Hessian, which is equal to negative 4, 2, 2, negative 6. The second order condition is, by the way, we're doing maximization here. So we don't have to like check both of them, just do the maximization. Second order condition should be that the Hessian is negative definite. That's the sufficient one. A matrix is negative definite if the top left is negative and the determinant is positive. That's all we have to check. So if you want to, I don't know why I do this. It helps with bigger matrixing. I say, just check the leading principal minors. The first leading principal minor is the first one. Negative 4 is negative. Check. That's good. The second leading principal minor. This would make sense if you had 3. Like, of course, there's only 2. It's kind of weird to write them out this way, but the second leading principal minor, that's the determinant of this whole thing. Negative 4 times negative 6 is positive 24. Minus 4 equals 20. It's positive, which is good. Is something unexpected there?
No, I forgot that leading principal minors aren't just following their negative. That's actually
The leading principal minor is the determinant
yeah.
of the top left section, however many rows and columns you are. The first one is 1 row, 1 column. Second one is 2 rows, 2 columns. Third one would be 3 rows and 3 columns if it were a matrix of that size. If there were 4 by 4, it's not even do that. But you might, to be honest, you might see some 3 by 3 Hessians, and you might be asked, is this a negative definite Hessian? Is this a positive definite Hessian? And I think the fastest way to tell whether it's positive definite or negative definite or neither, is to do this with the leading principal minors. Check the first one, which is just one number, the second one, which will be these four numbers, these two multiplied minus these two, and then the full thing, which would be the determinant of the full matrix. You'd have to use that method of this one times this one times this one times that. Sorry, that's me using my hands, but if you've forgotten that, how to do the determinant of a 3x3 matrix, I have a lot of stuff online. You can go back and look how to do that. Do you guys have any questions over? We've solved this problem. This is the problem. Solve the following maximization problem. We found this as a possible solution using the first order conditions, and we use this to confirm that the second order conditions for maximization are met. Done. By the way, we don't have to check for other ones. That's the only one, and it's a global max because the function is globally on concave, globally concave. I still get those mixed up. Yes,
That's what I was asking with the global.
it is because so whatever this function is, I didn't call it anything. That function f is sort of globally concave, and that implies it's a global max. Does that make sense? Imagine a hill, the top of the hill. If the rest of the function only keeps going down and down and down, it never curves back up, then that one point at the top of the hill has to be the global max. The only way it could not be a global max is just think of it as a mountain peak, that it curved and then there was another mountain peak somewhere else. But that would violate the concavity of f to curve back up to the other mountain peak. Did you have a comment? Somebody did, Marshall?
There's no variables in the Hessian if you say it's global.
Yep.
Okay.
That's a simple way to that's simple. And you might ask yourself, well, how often will there be no variables in the Hessian? Whenever these terms are always quadratic. If it gets to be cubic, then when you take the two derivatives, there'll still be some x's and y's. If the function is logarithmic, maybe there's some. If the function is anything but a simple kind of quadratic function, generally your Hessian is going to have some variables in it, some x's and some y's. And then it's relevant because what we didn't have to do was plug in x equals 3/2 and plug in y equals 1/2 into the Hessian. But you would have to do that, and I believe I have some examples in the future where you have to do that. Does that make sense?
Question.
Yeah.
Can you try to explain something more about the LP in leading principle?
This one?
The use of the two equations.
Yes. The first leading principal minor is simply this number because it is the first row and the first column of the Hessian.
Okay, I just mean the use of the two.
The use of it. Oh, okay. This is how we know that H is positive. No, sorry, negative definite. I always get these negative definite. If I give you a matrix and said, is this matrix negative definite? One way you could check is to see if the first leading principal minor was negative, the second was positive, alternates, etc. But we have that. This is negative. This is positive. And alternating like that is how we know. Maybe I should have written it this way. LPM1 is negative. LPM2 is positive. Good. If there were 3, it would have to be negative. But there's only 2. That's a good question. I think I skipped that. I skipped this logic a little bit, and I'm glad you asked. It's going to help everybody who's also a little unsure about that logic. Can we look at this answer? We got the right answer. It's a giant mess here, but y equals 1/2, equals 1/2. And also the second order conditions are satisfied. I know you can't see that. Should we do another example? Here's a logarithmic one. Although I think it's okay. Let me skip ahead. Does it have a? Yeah, I think you do have to for this one. Let me can I erase and we'll do it. Another one. I mean, we're going to do the same thing, just a different example, different function. Repetition. It's always good for learning. Can you read that? Not quite. The function is the natural log of x plus y plus 1. By the way, I know that you would have a problem, but these are always positive, so this is always positive. Minus x squared minus, is that a 2y squared? It is. We're trying to maximize this. Okay. Let's do exactly what we did before, but now for this new function. Anybody want to tell me the first order conditions?
One over the x plus y
Very good.
minus.
Very good. And of course, that's equal to 0. Very good. Second one. I'll assume you know it. That's the same thing here in the denominator. But now it's minus 4. Y equals 0. Here are our two equations with two unknowns. Now it's up to us to use algebra to solve this. We can do that. We know algebra. 626. Got time? Anybody have like a good idea for how to do it? You know, there's something I often do when I see things like this. When I see, ooh, I see the same thing in both. Light bulb goes off in my head like, let's use that. Let's solve for that. The fact that that appears in both, we can use that. When I say solve for, I basically mean that equals something. That's what I mean by solve for. So 1 over x plus y plus 1 equals 2x. But 1 plus x plus y plus 1 also equals 4y. This is a shortcut. If you're ever solving these first order conditions and you see some big chunk, big term that's the same in both, just leave it. Don't try to like solve, don't try to like expand it out and get all these other terms. No, just leave it. Set it equal to something, and then what you have are these other two things that are equal to each other. Is that an okay shortcut that I just did? What do we know? 2x equals 4y. In other words, x equals 2y. Now let's substitute that in. Let's substitute that in to either one. Which one do you want to do? FOC 1 or 2? Doesn't matter. In 1. Okay, let's take 1. FOC 1 now becomes, once I plug in x equals 2y, it becomes 1 over x. Oops. I'm going to replace x with 2y, pardon me. 2y plus y plus 1 minus, no, not 2x, but 4y equals 0. We can solve this for y. We'll get something like 1 over 3y plus 1 equals 4y. Or in other words, 1 equals, I'm going to multiply these all together and get 12y squared plus 4y. I'm going to subtract 1 from both sides and get a quadratic equation. Everyone's favorite type of equation, quadratic. You guys have the quadratic formula memorized? Quadratic formula? You do? Let's use it. I don't see any better way. Is there a better way to do this?
You can factor it, it's not bad.
I'll factor it. Okay.
Leave the square, negate yourself.
I have
So you really would factor this if you saw this and you were like, what's the fastest way to do it? You do factoring?
Cause the numbers are simple and I know 4 goes into 12, so I can guess it's easy.
But if it wasn't so straightforward, then I'd go for the longer.
Why don't I see it? Why don't I? It's obviously 6 and 2. Okay. And they differ by 4. That's what you noticed. Okay. Would you want to do that? We can do it. Do you guys know what we mean by factoring? It's like high school algebra. You don't.
I know it's mean by factoring, but I'm
What?
not sure the 6 and
Now,
2 come
we
from.
don't middle down.
Middle term breaking. Okay.
Yeah, that's another way to do it. That's completing
Like-
the square.
Oh, okay.
Oh, wait, I
Is that just?
I automatically use the quadratic formula.
It's always right.
It's always right, and it's just so fast for me because I've always used it. But I get what you're saying. There are these other ways to solve a quadratic problem, and factoring will work here. 6y
Minus 1.
minus 1. Okay, I'll take your word for it. And then 2y plus 1. Is that going to work? Yeah, because that'll make the 4 positive. That should equal 0. Agreed? And from this term, we will get y equals 1/6. And from this term, we will get y equals negative 1/2. Let me say, very good. So there's two. I know I don't really like when this equal sign like this. It's okay, but I usually say it's like one of these two. You know. I also know what you mean if you say equals. But we have two possibilities for y. More importantly, though, they correspond to x's in this way. If I know y, I can find x as being equal to double that y, but they correspond. I don't want you to think that either y is okay with either x, right? This y goes with 1/3, right? This y goes with -1. Agreed? So that's why I kind of like to say that xy is equal to, because this gets the ordered pair element of it, that it's not just any old x and any old y, it's this particular x 1/3, 1/6, or -1, -1/2. I'm going to check that.
A question?
Sorry?
How about we go with the condition that x and y are?
Ah, very good. Very good. X and Y have to be positive. So this one is gone. This one is gone. I forgot my own problem. Very good.
Okay.
Yep. Yeah, and if you tried to put negative numbers in here, this would explode. You can't, it would be imaginary. You can't take the natural log of a negative number.
Well. Actually, no, never mind, it's -1. I thought. That's-
Yeah.
I said, well, negative 1/2, but log of 1/2.
Yeah, it's not defined on the reals. In the complex plane, it's defined, but we're not working with that. Okay, thank you for whoever brought that up. Was it you? Thanks. Jeremiah, right?
Yeah.
Because the problem said that x and y have to be positive, we can just eliminate this as a possibility. We know if there is a maximum, it's got to be this. We're not done yet, though. Let's look at the second order conditions. Let's look at the second order conditions. And that is, we need to now, this will be the first time we actually have to run through some stuff just to get these second order derivatives. They're not going to be just simple and obvious. Anybody want to do that with me? What I really want is to get a formula for f(x)(x), which is the derivative of this with respect to x. What do you think it is?
Quotient rule.
Quotient rule?
Um,
Not quite, because there's nothing on the top.
Yeah, I guess we don't need to do it.
Yeah, just use the power rule. Something to the
Yeah.
-1 power becomes -1 times the thing to the -2 power. So 1 over x plus y plus 1 squared. And the -2 becomes, sorry, -2. I don't know why that doesn't look very good. I don't love how I wrote that. You can see that? Fxx is this. Want to do I'll do fxy next, which is the cross partial, or this with respect to y. That's just going to be -1 over x plus y plus 1 quantity squared. There's no other term here. And then for fyy, it's going to be this whole thing. But there's a -4, I believe. This is just me writing out the second order derivatives. It's not really the second order condition yet until we find that Hessian and we check, because it's a maximum, that the top left is negative and the determinant is positive. At the point 1/3, 1/6. Not everywhere. Doesn't have to be that everywhere, but it does. We're really just checking at this point 1/3, 1/6. And in fact, we're free to put that in whenever we want. We could put it in right now, or we could write out the Hessian and then plug in these numbers. Do you care? Any preferences? Put them in right now? It's not that complicated, but it might save us a little time.
Well, for fxy, the rest aren't too difficult.
Okay, but so yes, we are thinking of, let's plug in the numbers here. See, the reason not to do that is if there were multiple ones of these. And you've plugged it in and now you proceed. Now you have to check for another one. You kind of have to go back. But whatever, it doesn't matter. Okay, I'm gonna do it. I'm gonna plug in x equals 1/3, y equals 1/6, and getting -1 over 1/3 plus 1/6 plus 1. 3/2 squared. I'll leave it. Are we trusting him that 1 plus 1/3 plus 1/6 is 3/2? I think it's good.
Yeah.
And his name is Jerome, so I know his name. May forget it a little bit, but I always fine. I always remember it eventually. It looks good. And now -2. I would maybe like to simplify that a little bit more if we could. This is 9/4. The reciprocal of 9/4 is 4/9. We have -4/9 -2. Well, 2 is also 18/9. So this is equal to -22/9. Right. So we'll start building up our Hessian. Our Hessian equals, the top left is going to be -22/9. Granted, it's not this everywhere. This is the Hessian. If you like, I don't know, if this is helpful for you, this is Hessian evaluated at the point 1/3, 1/3, 1/6. You don't have to do that. It's just, it's just this idea that this isn't the Hessian at all points of x and y, just at this particular point. Okay. Well, we already had this part here, which was -4/9. So we can write that here and here. I think. Agreed? This part for fxy, which is also equal to fyx, that is just this first term without the -2, which is -4/9. Is that right? You guess right. Good.
Yeah.
Now fyy, we have the -4/9 -4, which is also 36/9, which is -40/9. I can already tell we're going to be good here. So the second order conditions are, the first leading principal minor should be negative. We can check that. It's true. Bing. this, oh, there's a 1 there. The second leading principal minor should be positive. Can we check that? Negative 22 times negative 40 for 9 minus 4 ninths squared. I can tell that's positive. I can tell it's positive because 22 and 40 are both bigger than 4. But if you wanted to check that just yourself, you could do it. But bing again for this. The second order conditions for maximization are satisfied. So this point here, 1/3, 1/6, not just the necessary, but the sufficient condition. So we are absolutely sure this is at least a local max. Are we sure it's a global max? Not really. Not really. Well, yeah, what we can say is that there are no other maxima.
All because the bottom, because the denominator is squared in fxy, fxx, fy.
What we could have done is left in the x's and y's and tried to say something about the concavity of the Hessian matrix everywhere, but we didn't do that. We used Manour's method, which was to plug in the numbers, and now we can't check to see if the Hessian is everywhere. Thanks a lot, Manour. Let's see.
The Hessian matrix should always have negative terms.
Yeah. By the way, in my on the slides, I don't bother to say whether it's a global or I say it is a local maximum. You can take a look. Oops. You can take a look at what I said about this problem. Same thing that we did here. Same numbers. It's indeed a local max. Yeah, I put local in there. To convince yourself that this was a global max, you would have to look at how the function behaves as you go farther and farther from this point, 1/3, 1/6. And of course you could convince yourself of it, I think, but it would take some doing. I'm not really teaching you that technique here to sort of take a potential local max and prove that it's a global max. Although, I don't know. It's not a very scientific way to do it, but the squared function grows a lot faster than the log function, right? So these negatives, as x and y both get larger and larger, it's never going to find another maximum besides this one. I just know for sure because how I know how this quadratic functions versus logarithmic functions grow. But like I said, that's not a very rigorous proof. That's more of a hand waving type proof. But I'm not asking you to do a rigorous proof for a problem like this. What should we do? 2 more minutes. Do you guys have any other questions about the quiz? I sort of think these types of problems are very likely to be on the quiz, like the types that we just did. A function with 2 variables, x and y, and I ask you to solve either a maximization or a minimization problem. And you know what to do. You can take that first order conditions, the 2 partial derivatives, set them equal to 0. Now you have 2 equations, and you can solve those for x and y. Now you can look at the second order conditions to see, is it indeed a max or a min, based on whether the Hessian is positive definite or negative definite, or neither. Yeah.
For the quiz,
Yeah.
can we do the third thing?
Oh, well, we're out of time today.
I mean, we be able to solve it by.
Oh no, not all of it. But some of it, yes. Sorry, let me help you out there by maybe going through some of these. No, not this one. This one, yes, you could. It'll take you longer, I think, to do. Well, maybe. It's actually all quadratic. You just have a lot of quadratic stuff in there. So the Hessians will be constants. That's good. The first order conditions will be linear functions. That's good. But this is just maximization problem with two choice variables, Q1 and Q2. So yeah, you could do this. The third problem, it's a little bit more philosophical here, this third problem. It's about, the real question is there a difference between this and this? I mean, you can think about that if you want. It's kind of an odd question to ask on a quiz, but the only difference between this and this is whether the person gets to choose Q or whether the person just allows Q to be the profit maximizing choice of Q given X. And you think of the person choosing X as a policymaker and the person choosing Q as a profit maximizing business firm. So you tell me right now, what do you think? Do you think these are the same or different? The X which maximizes this, is that the same as the X which maximizes this? It should be the same? Interesting. So it might be the same, it might be different. So it's not the case that it's always the same. Were you saying that it was always the same? Because that's not true. What matters is, so the question is, will it always result in the same answer for X? You have a maximization problem where the government chooses X, as opposed to the problem where the government chooses Q and X. It's only the case if the firm's interests are aligned with the government's. In other words, if the firm and the government have different interests for what Q should be with respect to X, then these two answers are going to be different. Because here, when you choose X and the firm chooses Q, if they're not going to choose exactly the same thing that me as the government would choose, then this problem is different than this problem. Even though I can induce any level of Q that I want, that's sort of the paradox. The paradox here is optimization with two choice variables. It's sort of fundamentally different than optimization with just one choice variable, even if I can predict Q as a function of X. Because what I've lost is degree of freedom. That's the takeaway here. Here, it's like I have 2 degrees of freedom to choose both Q and X. Whereas here, I can only choose X and that determines Q, but that's really just 1 degree of freedom. All I can choose is X. And therefore, my welfare is not as good here as it would be here. That's a philosophical, not philosophical, it's about the intuition involved in maximization. So I guess I could ask you like an intuition type problem about maximization, like what's really going on here when you maximize a function with two choice variables. Yeah, I think you could do this one too, right? These are, here's the one with 3. I told you that I wouldn't give you a 3 bagger on the quiz. So you can look at it if you want, but this is not going to be on the quiz because there's X, Y, and Z. Any other questions? You guys good to go? I think we're past time. I have been recording this. I'm not sure how well the recording went. But if any of you want to see this recording, I can post it somewhere, or I could like link to it on Canvas. I'm gonna stop recording now.